Okay, so here's example 7. Now in this example, and I didn't draw because it's a little harder to draw these, especially with my lack of artistic talent. Says the inverse image can be structures other than lines, right? So that's what we're talking about here. So for this linear map, H is going from R3, so 3D, three-dimensional to two-dimensional, so R3 to R2 using this mapping, right? Now notice it's XX here, right? So the inverse image, so if we take any vector in R2, XX, we take the inverse image, we get the sets of planes, x0, x equal to 1, and so on, that are perpendicular to the x-axis. Okay? Because here, if x is 0, we get all the values of y and z when x is equal to 0. So that gives us a plane that's perpendicular at the point x equals 0, right? Or the x-axis at x equals 0, and so on. So we see that there is an analogy here. Okay? So now we're not going to describe how every homomorphism that we will use is an analogy, because the formal sense that we make of when we use the term, alike in that, or is a homomorphism exists such that, but the idea that a homomorphism between two spaces expresses how the domain's vectors fall into classes that act like the range's vectors is a good way to view a homomorphism, or to view homomorphisms. Now, the other reason why we're not going to look at all homomorphisms, and we're not going to treat all of the homomorphisms, is that they become harder to draw. Especially if we look at polynomials. Okay? But there's nothing wrong with leveraging spaces that we can draw, especially from the examples that we've done so far, to draw two insights. The first insight is that in all of the examples, the three examples, the inverse image of the range's 0 vector is a line or plane through the origin. It is there for a subspace of the domain. Okay, and so we're going to introduce in the next video a lemma that we're going to use, and then we'll introduce another definition and move on. All right. Have a great day.